Hi, everybody. This is a topic that I always like talking about. Unfortunately, it's one that can go off in 100 different directions and tangents, so please feel free to enter any questions that you like to. We've got a full agenda, so I'm going to kick it right off. We're going to talk about, we're going to start at the very bottom, but we're going to move fast. We're going to talk about electrical power and the single-phase wattmeter, develop measurement of reactive power and power factor. We'll transition from single-phase to three-phase, talk about Y-connected lines, the importance of balance regarding the measurement of three-phase power. I will go off on a little tangent about the 2.5 element wattmeter to illustrate the importance of balance. And then we will develop how delta connected lines only require 2 single-phase wattmeters or a 2-element three-phase wattmeter to measure the total power. One of the tangents that suggests is the way that a the way that a 2-element wattmeter can be used for center grounded 120/240. I know most of the attendees today aren't so much interested in measuring residential power, but we often get requests from customers how to use our meters in a substation to look at the station service power. And I think that's an interesting example, so we're going to talk about that for a couple of minutes. Finally, and hopefully it is a finale, this is a topic that honestly we get questions virtually 3 or 4 times a week about wiring, common wiring errors. What are the indications on a three-phase wattmeter that maybe a voltage is rolled or currents reverse polarized or something like that? How do I tell where the problem is? And this isn't because of sloppiness. This is generally because wires are either labeled wrong or not labeled, or somebody traced them from their source and didn't preserve the the association with the source. Anyway, those are the topics, and let's kick it right off. So starting right from the basics, we're talking about AC power now. So I like to start in the time domain. Looking at sine waves is a little more intuitive to me than looking at vectors, simply because this is the profile of the voltage and current as a function of time on any given conductor. We all know that when you multiply 2 sine waves in the time domain, you get a third sine wave. If the 2 sine waves that you're multiplying have the same frequency, the resulting waveform will have twice the frequency, and it will typically be displaced above or below the axis depending on the relationship, the phase relationship of the 2 signals that you're multiplying. So the important thing about power when we shift from the time domain to vectors is that we're looking at averages. This is all the power that you've got. The blue line here, the VA, is all the power that's produced by the voltage and the current waveforms. We talk in terms of watts and VARs, but they're only significant to the extent that they resolve back into the VA. So looking at the VA has some importance all by itself. What I've got here is power that is moving from the source to the load for some portion of every cycle, but it's moving from the load to the source for some portion of every cycle. More of it is moving in one direction than the other, or you wouldn't have any useful work. Now, to break that up into what's useful and what's not useful, we like to divide out the VA into the sum of 2 other sine waves, not the product of the voltage and the current, but the sum of 2 sine waves, one of which is always moving in the same direction. Now, notice here, even though it's always moving in the same direction, it does still go down to 0. You've got no power actually moving for some portion of every cycle. And the amount of power that's moving towards the load increases and decreases, but it never goes in the opposite direction. That's watts. VARs, on the other hand, is the amount of power that moves in both directions in exactly the equal amount. So on average, there is no transfer of power from the source to the load, but it moves back and forth between the source and the load, on average contributing nothing to useful work. But it's power that still needs to be generated and transmitted, and it increases the amount of current flow, which is why there are losses. So VARs is a very important part of three-phase power. So one of the things that we observe right away is that if the current is in phase with the voltage, the VA looks entirely like the watts. It's always above the axis. It's always moving in the same direction. We could make it always below the axis, moving in the opposite direction, simply by putting the voltage and the current 180 degrees out of phase. Then it just always is negative, just in a greater or lesser extent. If the phase relationship between the voltage and the current is exactly 90 degrees, then all of the VA looks like VARs. So we've got this relationship where the part of the VA that is in phase with the voltage is useful work, and the part of the VA that is perpendicular or 90 degrees out is all reactive power. Last time in part one, we spent some time looking at a mechanical analogy that I like to use because it represents this concept of the perpendicular nature of reactive power relative to active power. Perpendicular suggests to a lot of people the use of imaginary numbers, complex math, and all of a sudden people's eyes glaze over. But it's actually pretty intuitive when you think about it. If you have a car rolling on a wavy road, the amount of power the engine produces that moves the car forward is your useful work. But you still have to produce a certain amount of power to compress the springs. If the car is not moving vertically, the car itself is moving horizontally, and the springs are completely absorbing the waviness of the road, you can see how the engine still has to produce the amount of power that compresses the springs, but that power is returned to the engine as the springs expand on the downside of each slope. So the vertical or perpendicular motion is reactive, and the horizontal motion is active. And that's an analogy that I've used in deference to, our customers are more educated than the average person on the street. And I've always thought it was a little bit insulting to talk to a degreed engineer about watts and VARs being beer and foam because it's got no quantitative sense and it doesn't explain anything. But the perpendicular aspect of reactive and active power, I think, deserves some attention. Now, that suggests, how do we go about separating one sine wave that's displaced above or below the axis into the sum of two other sine waves, one being perpendicular, the other being in phase? Well, anybody who's had, high school trig recognizes that you can break the amps into two components. If you represent the time domain as a vector, you can show the amount of current that's in line with the voltage as the magnitude of the current times the cosine of the angle. Now that's straight out of the time domain. That phase angle that we're talking about is the delta t between the time that the voltage sine wave crosses going up, let's say, from the 0 point, to the time when the current crosses the axis going up. So that phi is really just milliseconds or microseconds translated into degrees, where 360-degree phase, one 360-degree wavelength is 16 2/3 milliseconds if you're working at 60 hertz, or 20 milliseconds if you're working at 50 hertz. So now we've got our I cosine phi being the part of the amps that's in phase with the voltage. And the corollary, of course, is I sine phi, which is the proportion of the current that is perpendicular to the volts. This makes it very easy to multiply the portion of the current that's in phase with the volts times the volts. Don't even need vectors to do this. You simply multiply the magnitude of that component with the voltage, and you get P equals V times I cosine phi, where I cosine phi is the proportion of the current that's in phase with it. It plots along the same axis. So if you're looking at the time domain and you're translating the time domain into a polar plot so that you can represent the vectors, you see everything along the same axis. Multiplying the perpendicular vector, which is I sine phi, which is the portion of the current that is exactly out of phase with the 90 degrees out of phase with the voltage, you get a new vector, which is VI sine phi, but I don't see the VARs plotted on this graph. Why don't I see the VARs plotted on this graph? Well, up until now, everything we've been talking about has been in the XY plane, and the XY plane is the real plane. But when you multiply perpendicular vectors, this is where the resulting vector is perpendicular to the plane containing the voltage and the current. So now we've got a new axis, a z-axis, that projects out from the page. We call that z-axis the imaginary axis, which is, let's face it, if you're going to be an electrical engineer, there comes a point where you can't completely avoid talking about imaginary numbers and complex math. So here's where it moves into that domain. So you can't plot the volts and the amps vectors on the same plane that you plot the watts and the VARs. You may have noticed a lot of times we see this XY plane used to represent volts and amps, and we see an XY plane used to represent watts, VARs, and VA. But they're not the same plane. You can't plot the voltage and the current on the watts and VARs plane because the watts and VARs plane is the XZ plane and not the XY plane. So on the one hand, as long as you're in the XY plane, the vectors that you're looking at rotate counterclockwise, and you'll see the sequence of voltage and current, but you don't see the VARs. You could see the watts, that would be rotating, but you have to move into the XZ plane to see the VARs. Now, this perpendicular relationship that we keep coming back to, and which is why I thought, the mechanical analogy, why perpendicular, everything comes down to, a perpendicular axis. And this isn't what I would call, entirely theoretical. This is very practical. This is an actual 90-degree angle. So the way we've traditionally measured watts is by using two windings, a moving voltage coil and a stationary current coil, where the amount of the magnetic field that is parallel or in phase produces a torque against a spring that is proportional to the voltage times the amount of current that is in phase with the voltage. And if you shift the alignment of the magnetic fields by 90 degrees, that makes the same meter produce torque proportional to the reactive power toward the VARs. So this 90-degree relationship comes into, some significance. In terms of electronic meters, we no longer have to deal with torque. We no longer have to deal with magnetic fields. What we can do is we can digitally sample the voltage and current waveforms and use digital signal processing to calculate from the time domain, the samples in the time domain, we can calculate the vectors that represent the voltage and the current, and we can easily do the vector math that calculates the watts, the VARs, the VA, the power factor. All those things can be done with relatively simple vector math. And that's easily done with a microprocessor. So this is where we define the element. So a single-phase wattmeter is an element. Whenever we talk about three-phase power, we're talking about either a two-element or a three-element meter. But I'd like to emphasize very strenuously that when I say the word element in that context, I'm always referring exactly to this functional block, this single-phase wattmeter. Single-phase VAR meter is the same thing with a 90-degree phase shift, so it's still the same function. Power factor is simply the ratio of the watts divided by the VA, so the mathematical relationship is all very straightforward. But the element is the element, and nothing changes. We don't do any magic between phases when we talk about a three-phase meter. So the first step of increasing complexity from the single-phase wattmeter is essentially the Y-connected three-phase line, on which the total power can be measured with a three-element wattmeter. So a three-element wattmeter simply passes the current. Now, let me take a step back. I am deliberately not showing the CTs and the PTs where they would normally be in a substation. I'm simply showing the current and the voltage. If you can imagine the conductors that I'm showing for A, B, C, and neutral as being, the secondary side of CTs and PTs in all cases, it eliminates a lot of complexity in the drawing, and it just makes it easier to focus on the concept. So in a three-element wattmeter, you're passing the current through the current element on each of the three phases, and the three voltages are exact analogies to the single-phase wattmeter, where you're looking at the voltage of each phase relative to a common ground. That ground, that could be neutral. The neutral doesn't have to be ground, but they all have to be referenced to the same, it's like the high side relative to the same common. So the voltage element of a wattmeter is always a very high impedance, so that the connection from phase to ground looks like an open circuit. That's what makes an ideal voltmeter. It's what makes the voltage part of a wattmeter look like an ideal wattmeter. The current element has to look like a short circuit. So when you pass the current through the current element in a wattmeter or an ammeter, it doesn't have any impact on the current that it's measuring. It doesn't place a resistance across it. So if you treat the current element in each of these as a short circuit and the voltage element as an open circuit, you'll be able to follow along these little block diagrams a lot easier. So I don't think a lot of explanation needs to go into why the sum of the A phase element plus the B phase element plus the C phase element equals the total amount of power that is consumed by the load. I think we can stipulate that moving forward as intuitive. Now, I'm going to go off on a tangent here and talk about a 2.5 element meter. And I'm going to talk about a 2.5 element three-phase wattmeter using terminology that I've come to understand is not globally recognized. I've done some Google searches for the Z coil. I have to apologize. I'll tell you where I got the terminology. I started working at Bytronics back in 1990 when we were still making electromechanical meters. And it was explained to me that a 2.5 element meter, three-phase meter, was the same as a 3-element meter, except that it used a Z coil to produce the missing phase when only 2-phase PTs were available. Now, what I'm getting at here is it's a Y-connected 3-element meter where you connect the A to neutral voltage on one coil. You connect the C to neutral voltage on a second coil. And because of the shape of the core, there's an internal, there's a transformer inside the 2.5 element wattmeter that produces a voltage that is proportional to the vector sum of the A to neutral plus the B to plus the C to neutral It inverts the polarity, and that results into a, let's call it a synthesized beta neutral voltage. All right, that begs the question, how safe is it to assume that the eta neutral voltage plus the theta neutral voltage will produce a vector that, when inverted, is exactly equal to the beta neutral voltage? Well, it works perfect when the voltage is balanced. But if the voltage isn't balanced, then it produces a vector that is not equal to the beta neutral voltage, and the meter falls apart. It doesn't work. So this is what we refer to as the presumption of balance. How good is the presumption that three-phase to neutral voltages will be in balance? Well, the closer you are to the source, the closer you are to the generator. If you're up in the transmission system, the source impedance is very low. The balance of the eta neutral, beta neutral, and theta neutral voltage is probably going to be very good. And the further down in voltage you go, the closer you get to the load, the more likely the voltage may deviate from balance. Now, here's the two things: the throwback to the 1990s, plus the significance of this being in the transmission system. In the 1990s, before CCVTs were very popular, CCVTs are generally a lot less expensive to produce for very high voltages than a conventional wound PT. So a conventional wound PT for a 500 kV substation is going to be a very expensive commodity. And if you've got a lot of transmission, being able to save 1 PT per station might just very well be a real savings on budget. And since you're up at 500 kV, 345 kV, 230 kV, you're in the transmission system, your source impedance is very low, the expectation of voltage balance is fairly high. So in a case like that, when there wasn't an alternative to an expensive wound PT, a lot of utilities would use 2.5 element three-phase wattmeters on Y-connected transmission lines to save the cost of 1 PT. The meter itself, remarkably, is more expensive when you're talking about an electromechanical meter, because not only does it still have to have the 3 elements that you would have in a 3-element meter, but it also has to have this internal Z-coil to produce the third voltage. It doesn't have to connect to the B-phase voltage because you're presuming the balance and it's determining that voltage internally, but the real only savings is on the PT. So, you know, for legacy purposes, and because we do still see them once in a while, we still manufacture meters. Even though they're electronic, we now calculate the vector sum of the eta neutral and the theta neutral voltage, and we multiply the fabricated, the synthesized B-phase voltage with the B-phase current. B-phase current still needs to be connected. So this is what's called a 2.5 element wattmeter. Notice that the terminology half element refers to an actual wattmeter that's only connected to the current. That's what makes it a half element. This is not the same thing as a 2-element. Well, I'm getting ahead of myself. We'll talk 2-element in the next couple of slides here. I skipped a slide. So, okay. This doesn't say anything that I didn't say in the last slide. It simply is the advantage comes to the savings of 1 PT. It's not a saving of the wattmeter itself. Now I'm going to move on, and I'm going to derive, in a conceptual way, the use of a 2-element wattmeter for measuring delta-connected 3-phase loads. So I borrowed this out of my university sophomore class circuit analysis textbook. citing the reference at the bottom of the page. But basically, he did such a good job of developing this concept that it's stuck with me for the last 35 years. And I think it's a good intuitive approach to use in the context of a webinar like this. So we start with something that we all agree is intuitive and well understood, which is the idea of a 3-element wattmeter. Notice that I've moved the neutral to the right of the 3 loads. That's arbitrary. I could just as easily have had the neutral at the bottom of the page with a conductor running back to the source. But the point is still the same. The voltage winding of every wattmeter goes from the line to the neutral point, and the neutral point for each of the 3 wattmeters is the same point. That's where we start. So this stands without further explanation as intuitive measurement of the total 3-phase watts. Now, here's where I have to take a step back. So I mentioned that the proof in my sophomore textbook is very beautiful and it's very intuitive, but it does go into the calculus behind this assumption. So I'm not going to go into the calculus in the context of this. I could do another presentation, wouldn't take very long for people who are interested, but it basically comes down to one assumption, and that is if there is no neutral current, no zero sequence unbalance in the current, then we can move the common reference point for all 3 voltages, for all 3 wattmeters. We can move that off of the neutral, and as long as we don't separate them, we keep a single point X, that's the reference for all 3, the voltage between that X point and the neutral point is no longer a factor in measuring the total of the 3 wattmeters to be the total 3-phase watts. Now, I'm not saying that that stands without proof. I'm on this slide specifically saying that requires proof before you can make that assumption, because it's not always true, and it's not intuitive that neutral current affects the common voltage point. I think that's the counterintuitive part. Why does the neutral current mean that I can move the voltage? Let's stipulate that that's a fact and prove it off the clock. So basically, once we've accepted that, there are a number of implications. So if X doesn't have to be on the neutral, if X, the common reference point for all 3 voltages, doesn't have to be on the neutral, then we can make that Vx to neutral any value we want. Why don't we make it the B-phase conductor? If we make it the B-phase conductor, a couple of things happen. So number one, the B-phase wattmeter is measuring the voltage from the B-phase conductor to the B-phase conductor, which is 0. And 0 volts times any amount of current is 0 watts. So the B-phase wattmeter will always read 0 as long as there's no neutral current. Remember, the whole premise of the 2-element wattmeter is that we're going to be using it on delta-connected systems. Delta doesn't have a neutral, so the assumption of no neutral current is safe whenever we're using it. Whenever we're using a 2-element wattmeter on a delta-connected line. So if the B-phase wattmeter falls out, then I'm left with 2 wattmeters. We'll call them element 1 and element 2. In this case, because we've moved the common point to the B-phase conductor, the reference for both the element 1 and the element 2 voltage coils is the B-phase conductor. So I'm no longer looking at A to neutral, I'm looking at A to B. And on my second element, I'm no longer looking at C to neutral, I'm looking at C to B. My B-phase wattmeter fell out, and the B-phase current, as you can see, from this diagram, doesn't enter into the calculation of 3-phase watts at all. Now that is not, I think, counterintuitive. That, I think, is intuitive when you look at it this way. If I've made the premise that I have no neutral current. Or in a delta-connected system, I have no neutral conductor, so there's no place else for the current to flow. Why do I have to measure 3 currents if the third current must, with no exceptions, be the vector sum of the other 2 currents? So the concept that I can measure the total watts of a delta-connected 3-phase load without any concern over the B-phase current is not counterintuitive when you consider that you're measuring the A-phase current and you're measuring the C-phase current, and the B-phase current has to be the sum of the other 2. And this is really the underlying key to the proof that we were talking about before, that there's no place else for the current to go. In fact, the phase-to-phase voltage, there's no other place for the phase-to-phase voltage to be. If I know A to B and I know C to B, then I know A to C. They have to sum. So this is why 2 wattmeters works perfectly well for the sum of the 3-phase total power. That's going to be true as long as we don't violate the assumption no neutral current, no zero sequence unbalance. In other words, it's going to be true whether I have negative sequence unbalance on the voltage. There still can't be any zero sequence unbalance on the voltage, and whether there's negative sequence unbalance on the current. So this is a perfect representation of the 3-phase consumption of power by the load, regardless of the state of balance, as long as there's no zero sequence, and there's no zero sequence because there's no neutral conductor. This is what a 2-element wattmeter would look like then. You notice by comparison to the 2.5 wattmeter, or the 2.5 element meter that I showed you a few slides ago, this doesn't have a half element. This is exactly 2 meters, and you don't have to connect to the B-phase current. So let's see. Oh, okay, I see what I'm saying in this slide. So if I let's see, where was I going with this? There are multifunction meters. We make multifunction meters at Biotronics. There are multifunction meters on the market that measure the total power on delta-connected systems that use the 2 wattmeter method. So they only need the A-phase current, the C-phase current, and the A, B, and C-phase voltage. But they have terminals where you can connect the B-phase current. Why do you do that? Well, you do that because it's a multifunction meter, and you want to be able to display the A-phase current, the B-phase current, and the C-phase current. So if you have terminals to bring in the B-phase current, I can show the 3-phase current on this multifunction meter, even though the B-phase current does not enter into the calculation of the total watts. The next question, I think, is suggested by this is the presence of the neutral line. You see between these 2 slides, the presence of a neutral conductor doesn't really change so much the usefulness of a 2-element wattmeter. You could use a 2-element wattmeter if you had a neutral conductor, as long as there's no current flowing through it. So what I'm suggesting is, by comparison to a 2.5 element meter, where the underlying assumption is the voltage must be in balance for it to work, compared to a 2 wattmeter method, the 2-element meter, where the assumption is no zero sequence current, no neutral current, which of those presumptions of balance do you think is more restrictive? I think it's a lot easier, since the voltage is supplied and regulated. The expectation of voltage balance, particularly in high voltage lines, is a reasonable assumption. But the expectation of current balance, particularly when we distinguish negative sequence from zero sequence imbalance, the assumption that you will have no loads that cause the current to have zero sequence imbalance, I think, is not usually a safe assumption as long as there's a neutral conductor to carry it. If there's no neutral conductor to carry it, you've got a delta connected line, which is why delta connected meters are used, like 2-element wattmeters can be used on delta connected lines. So the next couple of slides we're going to run through very quickly, just as a refresher. What is it the 2-element wattmeter is looking at? I'm going to use the vector equivalent to the derivation that I showed you in the previous couple of slides. I'm starting with a 3-phase Y-connected system. I'm showing the voltage and the current. I'm going to assert that even though I have 3 voltages from A to neutral, B to neutral, and C to neutral, that does not change the fact that if you were to measure the voltage from A to B, B to C, and C to A, that those voltages exist, and that if you were to pair up the phase-to-phase voltages that I measure this way with the currents that I measured in the previous slide, I'm going to get the same amount of watts for the same amount of volts and the same amount of amps, whether I measure the voltage from phase to phase or whether I measure it from phase to neutral. These two systems will produce the same number of watts, same amount of watts. Now I'm transposing the 3 phase-to-phase vectors to the origin. You see they retain their 120-degree phase relationship to each other, but they take on a 30-degree phase relationship to the current. And again, the assertion is I haven't changed the current. All I'm doing is looking, I still haven't even changed from a Y-connected system. I'm simply looking at the phase-to-phase voltage and the line current, which doesn't change just by virtue of the fact that I'm measuring the voltage from phase to phase. Now, since the 2-element wattmeter only uses only uses 2 voltages and it only uses 2 currents, in this slide I've eliminated the voltage and the current that I'm not using in the 2-element meter, and I'm recognizing what we said in the earlier slide, that the element 2 voltage is no longer B to C, which is the more intuitive way of expressing the phase-to-phase voltage. We usually talk about A to B, B to C, and C to A. But the wattmeter is now looking for the voltage of the C phase. Remember, element 2 is connected to the C phase as hot. And the low side is now the B phase. So what we're looking at isn't VB to C, it's VC to B, which is why I invert the vector. Now we're starting to see a little bit of symmetry. These are my 2 single-phase wattmeter elements that produce watts based on the A to B voltage times the A phase current and the C to B voltage times the C phase current. And you'll notice in this diagram that the portion, remember we started with unity power factor. There was no phase angle between the voltage and the current in the Y-connected system we started with. So you'll notice in this that the part of the current which is in phase with the respective voltage is going to be additive because it's both of them are in the same direction. They go in the direction of the voltage. But the VARs on a 2-element wattmeter where the voltage and current are in phase with each other, the VARs are non-zero because you've got an inherent 30-degree phase shift, but they're in opposite directions. So the VARs on the element 1 and the VARs on the element 2 are equal in magnitude but opposite in direction. They cancel each other out, and I get 0 VARs because my voltage and current was in phase, but I get actual watts because I had current and voltage in phase. Now all I'm doing in the next slide is I'm rotating everything so that the A to B voltage shows as the horizontal axis, which resolves into the typical phasor diagram for a delta connected line. All right, take out the neutral, take out the neutral conductor, take out the line to neutral voltages. This is what you're going to see on a delta connected line. This is only what you're going to see on a delta connected line if you're looking at VC to B. If you were looking at VB to C, you would see it 120 degrees in the lower left-hand corner of the screen. But this is the 60-degree relationship that you typically see when you're looking at the inputs on a 2-element wattmeter. So I think that's an illustrative sequence of vector slides for something that's not otherwise intuitive. So next I'm moving on to a special case of the 2-element wattmeter. Everybody should recognize here, without looking at the meter or the meter connections, what you see here is either, if you care to think of it as a residential load, where I'm using a distribution transformer as the source, center tapped, maybe a 13.2 phase-to-phase, 8 kV line-to-ground distribution transformer with a 240-volt secondary with a center tap giving you 120 degrees with a 180-degree phase relationship between line 1 and line 2. Now that doesn't look like a delta. But if I ignore the source and just look at the load, you would have a hard time distinguishing that load from a delta connected load. If I was sourcing this with three-phase delta generator, this would be exactly the same thing as a delta connected line. And we said a few slides ago that it didn't matter how much imbalance there is on the voltage, and it doesn't matter how much negative sequence imbalance there is on the current. Remember, as long as I don't have a fourth conductor, I can have 3 conductors. It doesn't matter that the one is at the center tap, because if this were A, B, and C, if there was a phase angle between my line 1 and my line 2, it would still have that common B phase in the middle. So I don't have a fourth conductor for current to flow. I have no zero sequence imbalance. Therefore, a 2-element wattmeter will always work on station service, which is where you typically see them used. You don't typically see somebody using a SCADA meter for residential service, but in a substation, it might be very handy to monitor your station service load using a 2-element wattmeter that's connected to SCADA. So it's a special case, and I think it's interesting because residential kilowatt-hour revenue meters are wired the same way. It's a single-phase wattmeter, but you have to contend, even in a single-phase kilowatt-hour meter, you have to contend with the fact that it's got a center tap grounded neutral and 3 conductors. It's not a single-phase wattmeter. You don't use a single-element wattmeter for residential loads. You use a 2-element watt-hour meter to do this. Now, the form factor, varies. That's a matter for revenue manufacturers to be concerned with. But this is the underlying technology behind residential and station service metering. Actually, I probably should have shown this slide before the last one. This is just to say that you can't distinguish center tap single phase from a delta. If you don't know anything about the source, and all you know is the load, it looks very much like a delta. All right, that's all the derivation that I have for this presentation. The remainder of the presentation I think is interesting. I think it's the finale. It has a lot of practical implications, and it will be useful to introduce a 3-phase watt calculator that I've been using for the last 30 years. I built it in Microsoft Excel, and it basically just does the vector math that simulates a 3-element wattmeter on one tab and a 2-element wattmeter on the second tab. I type in the voltage and the current and the phase angles, and it tells me what the per phase watts are, what the total watts are, and I can use that to dial in 180-degree phase shift if someone wants to simulate what the results would be if he inverted the polarity of one of the connections, unintentionally, obviously, it's a wiring error, or if he rolls the phases. Now, once you recognize that, first of all, these wiring errors are fairly common, and secondly, that they're easy to simulate, but they're hard to remember. Having this calculator in your hip pocket when you see something that you don't expect might be very handy. And tabulating the results might be a nice check if I'm connecting a wattmeter in a substation and I see a pattern that isn't obvious what it indicates, how to correct it easily. So basically on this slide what I'm saying is it's easier to invert the polarity of a current connection because the current goes into the meter on one terminal and it comes out of the meter on another terminal. And if you reverse the connection of those two terminals, you would invert the polarity. It's harder to do that with the voltage because one of the three conductors is ground and the other three conductors are hot. It's very easy to see which one's neutral, with a handheld fluke. It's not as obvious which one's A, which one's B, and which one's C, so it's very easy to rotate the phases on the voltage. It's less easy to rotate the three phases of the current because you would have to have more conductors labeled wrong, and it's just less likely. So let's see what all the combinations and permutations of these two wiring errors turn out to be. So let's start with three-element meters because they're more intuitive. So let's suppose, simple case, the polarity of one of the phase currents is inverted on a three-element meter that's carrying an otherwise approximately balanced load with pretty close to unity power factor, sort of an ideal case. I want to call to your attention the first bullet on every single slide for the rest of this presentation is going to be all three-phase voltages and currents look exactly like you would expect. When you invert the polarity or you rotate the phases, the currents will not indicate that you have a problem. Only the watts will indicate you have a problem, and the VARs and the power factor and the per phase watts will tell you which one to look at. So all three-phase voltage and currents look exactly as you'd expect. The neutral current, in this case, turns out to be 2 times the phase current. I guess that's not intuitive. I wouldn't have known that if I didn't plug it into the calculator. I'll show you that in the next slide. The per phase and total VA all look normal. Well, if the voltage and the current look normal and the VA doesn't have a sign, then the VA per phase and total are all going to look normal. The total watts and the total VARs read 1/3 of their expected value. Well, that's kind of intuitive because if I've inverted the polarity of one phase, then I've got 2 phases pointing in one direction, 1 phase pointing in the opposite direction. The 1 phase that's pointing in the wrong direction is going to cancel out one of the 2 phases that's pointed in the right direction. And what I'm left with is the 1 phase that's pointed in the right direction. So the total is going to be about 1/3 of what I expect. Beyond that, the actual power factor is near unity. The watts will look like 1/3 of the total VA. That's a good indicator because that's typically one of the things that you see on a multifunction meter when it scrolls through. The watts and the VARs of the 2 phases on the 2 phases read power flow in the expected direction, and the watts on the reversed phase read it in the opposite direction. If you display the per phase watts, you're going to see the sign, and that'll tell you which one to correct. So here is the right out of the 3-phase power calculator that we set up. I type in the input, the amount of voltage. I type in the phase angle. I type in the ratio so that I can see the values in primary and secondary values at the top. The lower half, the watts and the VARs, is only in primary units. And what I've done for the purposes of this demonstration is I simply picked out an amount of current that will cause the power to add up to 3 megawatts. It's 3-element meter, so 3 megawatts, 1 megawatt per phase. It's just illustrative. All the vector math is being done in the background. That's not the point of this presentation. The point of this presentation is to show you what happens when I do this. So if I were to type in a bias of 180 degrees on the A-phase current, I know that lines up with element 1 watts. That's not the point. The point is that this little phi-in cell is added into the current for A-phase current in the upper half of the page. So I don't have to change the relationship between the A-phase voltage and the A-phase current except the bias of 180 degrees, which is the result of having wired it backwards. So I can see 0, minus 120, and plus 120 as my 3-phase voltages, phase to neutral voltages. And on the phase to neutral current, I see the B and the C are correct. minus 120 and plus 120, just like the voltage. But on the A phase current, I have a 180-degree phase shift. The spreadsheet does the math, and the results are what you see below. So the resulting current, when you do the vector math between the three phase to neutral voltages, is about twice the per phase voltage. Like I said, that's not intuitive, but if you look at the vectors, it'll make sense. And the A phase watts is going to be basically exactly the opposite, the same magnitude with the opposite direction as the other two phases. You correct that, and you're back to business. It doesn't matter if I inverted the B phase or the C phase. As long as I'm only inverting one phase, it's going to have the same effect. All right, now I'm not going to go into this much detail and explanation on each of the permutations that follow, but this is the theory behind using the calculator to predict the outward indications of the different wiring errors that you see. So what happens if I reverse two phases on the three element meter and only one of the phases has the polarity correct? Well, think about it. What I've just done is I've reversed the direction of the entire power with only one element pointing in the opposite direction. So this is going to look very much like one phase with reverse polarity, except everything's going in the opposite direction. So voltage and current still looks normal. Residual current is still 2 times the phase current. The per phase and total VA still look like you'd expect. The watts and VARs still read 1/3 of the expected value. The watts is about 1/3 of the VA if you have good power factor. The watts and VARs on the one phase will read in the correct expected direction. The two that are wired wrong will read in the opposite direction. Corrective action, find out which two phases are reversed and correct them. So here's a normal scenario we start with. I invert the A and the B phase, or the B and the C phase, or the A and the C phase, doesn't matter which two I invert. By typing in the 180 in the bottom half of the page, you can see the A phase is now 180, and the B phase is now minus 120 plus 180, which equals 60, and the C phase is still plus 120. When you do the vector math, you now see the two inverted phases are minus, the third phase is plus. You still get twice the neutral current. You still get 1/3 of the total watts. The watts is 1/3 of the VA. All good indicators that if that's what you're looking at on a multifunction meter, that's the kind of wiring error that caused it. This is for comparison, just between having one phase inverted and having two phases inverted. You can flip back and forth and see what the difference is in the calculator. What happens if all three of them are reversed? Okay, all the voltage and current looks normal. The residual current looks normal. Per phase and total VARs, watts, VARs, and VA all look right, but the sign of the watts and VARs are both opposite. Corrective action might be to reverse all three phase currents, or the note at the bottom of the page, consult your company policy. Here's something we run into all the time. Some utilities want all of the power flowing into the bus to be positive and all of the power flowing out of the bus to be negative, so that the sum of the power into the bus, all of the inputs plus all of the outputs, equals 0. There's some merit to that. Other utilities want all of the power flowing from source to load to be positive and all of the power flowing from load to source to be negative. Now that's the opposite convention, but there's merit to that too. All depends what your objective is. So your company policy might be why the three phases are wired in reverse. You want to know that. If it turns out that you need to reverse all three phase currents, some meters have a configuration setting where with the check of a box in the settings in the configuration, you can invert the polarity because some utilities have an opposite convention for the signage of the watts and VARs going into and out of the bus. So if you've got that, like on an M650, you may be able to fix it just by checking that box in the settings. Here's what it looks like. Start with the normal case, invert all three phases, everything's normal, the power's just flowing in the opposite direction. Not necessarily an error unless it's conflicting with your company policy. Now what happens if we rotate the phases? Rotating the phases is a lot of fun. It's different from, you don't have 180, now you've got 120 degree phase shift. Now the watts and the VARs do different things because the effect of 120 degree phase shift on the sine and the cosine is completely different. So this is where it gets a little more interesting. And it's more common. It's very easy to swap an A and a B voltage connection terminal on a meter than it is to, invert a polarity or like that. So if one phase, if all three phases are rolled in the same direction. So A is on B is on C, and C is on A. Neutral is on neutral. I'm not going to deal with wiring errors where the neutral is on A and the B and the C are on neutral. That's less common. It can be ruled out with a fluke. If your neutral is hot, you've got a problem. Okay, so all three are rotated in the same direction. All three phase voltages and currents looks exactly normal. The neutral current looks like you would expect. The per phase and total VARs look normal. The VARs are greater than the watts. Okay, so here's the first thing that you're going to see that looks a little fishy. Typically, you're usually operating with pretty good power factor, so the watts are going to be substantially greater than the VARs. If you've rotated the phases, the VARs will be greater than the watts. The total three-phase watts will read about half of their expected value, and it'll have the opposite sign. That's because of the cosine of 120 is 0.5. Oh, and you want to take into consideration that if you have a non-unity power factor, 120 degrees may be a power factor of 0.5, but 125 degrees, 115 degrees, you incorporate the phase angle of the actual power factor into that 120 degree shift, and it may not be exactly half. So what you're looking for is about half here. What else would you see? All the power factors are going to be equal to about half. Corrective action. This is cool. I like this. So it occurred to me when I was thinking this through, you have to roll all three phases to correct it. So which direction do you go? Well, you really can't tell from the meter which direction is right, which direction is wrong. So what I'm suggesting is roll all three phases in either direction. If there's no change, you pick the wrong direction because you'll now have a meter where everything was rotated one phase in the opposite direction, and all of the symptoms will be exactly the same. But if you rotated it in the right direction, everything will go back to normal. So if you rotated it, if they were wrong to begin with because they were rotated one phase in the wrong direction, and you rotated a second phase in the wrong direction, and that didn't correct the problem, rotate it one more step in the same direction, and you've gone 360 degrees, you've corrected the problem. One step might have a fix, two steps, definite fix for the wiring error. Here's what it looks like with the calculator. We start with everything wired normally, and we go into 120 degree bias on all three phases. Now, I biased the currents rather than the voltage because of the way the spreadsheet works, but it doesn't matter if I rolled the voltage or the current. It's going to have the same effect on the watts and the VARs. So ignore the fact that it's the current that I'm showing rotated here. So what do I see? Neutral current is normal. The watts is about half of the VA. The power factor is half. The VARs are much greater than the watts. It's not going to be twice as much because the VARs are based on the sine of 120 degrees and the watts are based on the cosine of 120 degrees, which is completely different. But the indications that that's the nature of the wiring error are still pretty clear and easy to work backwards from the symptoms to the error. What if one phase is wired correctly but the other two are rolled? Okay, that's probably the most common wiring error we see when people call in asking, what happened. So in this case, all three phase voltage and current still look normal. The neutral current looks normal. The per phase and total VA look normal. The total watts and the total VARs will read 0. So they're basically going to cancel out. The per phase watts or VARs on the two flipped phases will add up to the watts or VARs on the correct phase, but with the opposite sign. That's because the power factor is now, minus 0.5. So identify the two connections that are flipped, flip them back, and you're fixed. Here's what it looks like. Here's a normal connection. I flipped two of them. I flipped them by 120 degrees because I'm flipping phase B and phase C. So now the B phase is where the C phase should be, minus 120. And the B phase is at plus, minus 240. What did I do there? Minus 120 is minus 240, which is plus 120, which is where the C phase should be. All I did is I forgot to subtract 360 to make it from 0 to minus 120. So it's correct. So the B phase angle is where the C phase should be, and the C phase angle is where the B phase should be. Those are the two wires that are flipped. This is what happens. The flipped phases have half and in the opposite direction of the correct phase, and it adds to 0. If you have your voltage and your current connected, showing the right value, and your watts and your VARs both look almost 0, that's a dead giveaway that somehow you flipped two PT connections to the meter. Now we move to two-element meters. So I want to at least take a minute to recognize that it's harder to determine what you did wrong from a two-element wattmeter than it is from a three-element wattmeter. Why is that? Well, there's no neutral current. There's no phase to neutral voltage. There's no per phase watts. There's just not a lot of, and if you were to plot the phase angles, you're going to see a 60-degree angle between the two voltages that come in instead of 120 degrees. And you're going to see a 30-degree phase angle between the voltage and the current when you have a good power factor. All of these things are counterintuitive when you're trying to figure out how did I wire, what should I be seeing, and how did I wire it wrong? All right, so let's look at a couple examples. There are fewer of these. We're almost done. Let's say one phase current, either A or C, because you only have two elements, is reversed. If you reverse the B phase, it wouldn't make any difference because the B phase doesn't enter into the watts. So all three phase, per phase voltage and per phase current will look exactly like you'd expect. The VARs will be greater than the watts, which is one indication you've got a problem. Total three-phase watts is a low number. It may be 0, but because the sign function moves very fast, the rate of change of the sign function near the 0 crossing is a lot faster than the cosine, which is at a peak near 0. So your power factor affects the VARs very much in this range. So your three-phase watts is low. It may be 0. But because of the power factor, it may not be exactly 0. Total three-phase VARs is equal to or nearly equal to the VA, which is the same thing as saying the watts is nearly 0 because of the phase shift. Because of the sensitivity to the sign and the fact that the sign is not symmetrical about the vertical axis at the 0 point. You cannot depend on the sign of the VARs to indicate which of the two elements is reversed. That won't be a good indication. So the corrective action in this case is let's see. Try either the A or the C phase current. Okay. Remember, you got to use a sliding block or a make before break test switch before changing any currents, but you can reverse the polarity on either the A phase or the C phase. If the total watts indicates the opposite of what you expected, you chose the wrong phase. If it goes back to normal, that's the fix, all in one step. So here's my two-element wattmeter. This is what the calculator shows me. Notice that I'm looking at V A to B and VC to B, not VB to C. So that's why this is going to have a 60-degree phase shift and not 120-degree phase shift. So what I've done here is I have, let's see, what did we say? The polarity of one current. Okay, so we have switched the current from a 30 degrees, oh, this is the normal wiring. That's right. I was saying this is right. I've got a 30-degree phase shift between the A-phase current and the VAB, and I've got a 30-degree phase shift between VC and VCB, like I showed in the vector diagram a few slides ago. It should be showing me, I picked an amount of current that adds up to 2 megawatts just because it's a 2-element meter and it's a good indicator of where your problem is. Now let's flip the polarity by 180 degrees of one of the phases. So I flipped from minus 30 degrees on the A-phase current, I flipped it to 150 degrees on the A-phase current. And what happened is my total watts went from 2 megawatts to 0. My total megavars went from 0 to a number that is approximately equal to the VA in the opposite direction. And those are my two indicators that I've got a problem and what the problem is. So if I was to reverse one of the phases and it showed the right number with a negative sign, that would be the wrong phase. If it shows the right number with the right sign, that would be the right phase, and it would have corrected the problem. And that's all the indication you're going to get on a 2-element wattmeter. Suppose the polarity of both the A phase and the C phase are reversed on a 2-element meter carrying an approximately balanced load. Well, this is much like you would expect. If you reverse both elements, the polarity of both elements, all you're doing is showing power moving in the opposite direction. The same as changing the polarity on all 3 phases of a 3-element meter. It may be the policy of your company that power into the bus plus power out of the bus must equal 0. So you have to consider that that might be the explanation. But here's what it would look like if it was wired that way. So I go from minus 30 and 90 as my current phase angles. I go to 150 and 270. And the total watts and the total VARs are the right magnitude, but the opposite direction, which is what you would expect if power was flowing in the opposite direction or if the policy of your company was to show a minus sign. Indication the A and C phase voltages are rolled. All 3 phase voltages and currents look normal. The total 3-phase watts and VARs read 0, or nearly 0. So you can leave the B phase voltage alone because it's in a 2-element wattmeter, it's usually the B phase voltage that's grounded. So for the same reason that you can always tell if I've rolled the neutral, because the neutral is going to be ground and the other 2 conductors are going to be hot, you can always tell that the B phase voltage has to be ground. So the 2 hot lines have to be A and C. So leave the B phase voltage alone and swap the A and C phase conductors on their PT terminals on the wattmeter. Here's your normal situation, and here's what happens if I reverse them. Notice in this case, I'm just switching the 60-degree phase shift on the VAB and the 0-degree on the AB and the 60 on the CB. I'm switching the 2 of them in the error condition, and both the watts and the VARs add up to 0. And as they say, that concludes my prepared remarks. I have no more material for today. Are there any questions, please? Johannes, did anybody write any questions?
There is one. It's in Spanish. We'll get back to him in the writing, in the email.
Okay. I'd be happy to follow up in email. Google
Yes.
Translate works very well with Spanish.
Right.
And otherwise, that's everything I've got, Johannes.
All right. That was great. Thank you, Brian. So that's it for us for today. We have all the power hours posted on our Power Committee website. If you sign up, you can see all the power hours, documentations, application notes, all kinds of good stuff. With that, thank you for joining us, and we'll see you guys on our next power hour in a couple of weeks. Thank you.
Take care, everybody.